Alright, so in the previous video we talked about RSE, which is a measure of model accuracy, right? In this video we're going to talk about the second method. Second method, which is going to be the R-squared statistic. Cool. Why is there a second method? It is because the RSE, it provides what is called an absolute measure of lack of fit. RSE provides absolute measure of lack of fit, right? What this basically means is, do you remember that time we said the RSE for the advertising data is 3260 units, right? This is an absolute number. It is absolute, like it tells you like the actual deviation, like 3260 units. The problem with this is it is measured in the units of our y. It's measured in the units of our y. So it is not always clear what constitutes a good RSE. When we finished the last video, the debate was, okay, which level is going to be a good RSE and which one is a bad RSE? When you just look at 3260, is that a good number? Is that a bad number? We wouldn't know. So that is the use of them, R-squared statistics, right? So R-squared statistic is a proportion or a ratio. You can say it's a proportion or a ratio. Ratio of variance. It's a proportion or ratio of variance. Let's see what that means, right? What it implies is it always takes values between 0 and 1. 0 and 1, and is independent of the scale of y. Let's see why that is the case. So it is independent of the scale of y. It doesn't have these units like this, and it always takes the value between 0 and y because it is a proportion or a ratio. Remember, a ratio like 1/2, that's a ratio. 1/3 is a ratio. 10/15, that's a ratio, right? So it is always between 0 and 1, right? It is defined like this. R squared is equal to something called TSS minus RSS over TSS. What is this TSS that that I introduced now? So TSS is defined. It is defined as the total sum of squares. Total sum of squares, right? Let's look at what TSS does and the implication now for this equation, right? TSS measures total variance. It measures total variance in response y. So we can think of this TSS. Let me write it here. TSS. We can think of TSS as amount of variability in our data, or in our response, before we do the regression. Right? Before regression. What is the definition? Let me write the equation for TSS so you can see it nicely. The equation for TSS is just saying y. It is a summation of yi minus the mean y, like that. That is the equation for TSS. So it is the amount of variability in the response before we even do the regression. Before we do the regression, what is the variability in our data? So since we haven't done the regression, there's no prediction to subtract from. So we subtracted from the mean of our values, right? Then let's look at RSS. If you remember, our RSS is defined as yi minus y hat I squared, right? How do we define this? So this is what do you call this? Measure of variability after let's see, measure of variability that is left variability left after regression. Because let's explain some of these principles here, right? Especially this one, the measure of variability left after regression. What does that mean? If you remember our graph there, we had a line. We would get a line like this, isn't it? And then we had points there. And our R squared, basically, what our RSS, would now say, oh yeah, you have explained some variability using your green line, but there's still some left. These E's here. These E's are still left out. And those are now my RSS. They're the ones that are left, isn't it? The rest go into being explained using the what? Using the regression. We get rid of some variability. We are not talking about them now. But this regression line, the green line, takes away some variability. Regression does that, right? Regression takes some of that variability. But there's going to be some variability that's going to be left out. These ones here, these E's here. And those are the ones that are going to form my what? My RSS. So RSS is a measure of variability left after regression. Let me just say the E's, those ones. Cool. So now let's see what the top part means here. TSS minus RSS. So we are subtracting these two. What does that mean? This one was the amount of variability in response before regression. So this was the total amount of variability. Alright? That was the total amount of variability. Isn't it? So it was everything before we even do regression. That was all the variability that is there. Let me just write all variability. Right? We're saying all variability minus variability left after regression. Because we're doing TSS minus RSS, right? So what variability then do we get here? If this is the total variability, it means part of this is the variability due to regression. Part of it is the variability due to some other things in there. So there's going to be all the variability in here. And if we subtract the variability left after regression, what we are left with is, so this is equal to variability explained by regression. I hope you see that. This was the total variability, every variability, and then this is just variability left after regression. So the difference between the two is obviously variability that was taken out by regression when we did our RSS, isn't it? So the variability left after regression. So this is equal to TSS. TSS measures the amount of variability in the response that is explained or removed by performing the regression. So now let's look at our R squared. What does that imply then? Our R squared is saying TSS minus RSS over TSS. TSS is the total variability, right? The whole variability in the data. Cool. And then the top part, we're just saying TSS minus RSS is equal to the variability explained by regression. So here is going to be variability. When you say explained by regression, it means, oh yeah, there's a variability, but regression has taken care of that variability. So variability explained by regression. So can you see that this is going to be a proportion that is going to be, it's going to be between 0 and 1. Because variability explained by regression is part of total variability. So it's like 10. If the total variability is 10, variability explained by regression can either be 0 or go to 10, because 10 is going to be the maximum. It's the maximum because 10 is the total. It's total of everything. So which means this value is going to always be between either 0 and 1. It's going to be between 0 and 1. Right? So how is this a test of model accuracy? How is it? a test of model accuracy? Well, it is a test of model accuracy because if this variability that we did our regression, and our regression took out a lot of the variability or explained a lot of the variability, we look at our data like, yo, it's so variable. But when we use our regression, and regression explains a lot of that total variability, it means our regression model is very, very accurate, right? That's what it basically means. It means our regression is accurate. Imagine we're saying total variability is 10, and then our regression explains 8 variability of that. It means it's going to be 8 over 10, which is like 80%. So it means the variability that we're being shocked by in our data can be explained using regression. How good is that model? It means that model is 80% accurate, which is good, right? Which is very, very good. But then, if there's so much variability in our data, and when we apply regression, and you can only explain for 2 out of 10 is 20%. That is just a low number. It means our regression that we have applied here, our linear regression, is not sufficient. There's still some more variability that we need to explain. Maybe we need to use a better model that is not linear or simple linear regression, right? So basically, R squared that is close to 1 or 100%. So 8 over 10 is just 0.8, right? And 2 over 10 is 0.2. So R squared that is close to 1, it indicates that a large amount of variability in the response has been explained by the regression. A number close to 0, so we have this, and then we have another situation where it's close to 0, indicates that the regression did not explain much of the variability in the response. So this might occur because the linear model is wrong, or we have some variances that are in there that we cannot account for, right, using the linear model. So this one here would be happy if our R squared is close to 1. This one here, not so much. It means my model is a bit wrong. In the advertising data, our R squared is equal to 0.61. So what that basically means is just over 2/3. So just over 2/3 of the variability in cells. Variability in cells is explained by linear regression. And you remember here we're doing linear regression with what? Linear regression with on TV. So we're saying cells beta naught plus beta 1 times TV. So it means two-thirds of the variability in cells has been explained by that linear regression. So R squared is better than RSE, since unlike RSE that just tells you 3260. What does that mean? This one here, it will always lie between 0 and 1. So you can see if it's close to 1, you're happy. If it's close to 0, you're sad. You know what I mean? So still the challenge is, okay, how close should it be to 1? What is a good RSE? What is a good, not RSE, what is a good R squared for you to be happy that the model is accurate? What is a good R squared? So what people can do, let me delete everything now, so we can start on this page. I need to create like a bigger page, right? Okay, so if you've done a bit of statistics before, you know there's something called correlation, right? Correlation between two quantities. The correlation is given by this equation. Let me write there. It's a quite a scary looking equation. If you remember this in like statistics, it's going to be square root system. Yeah, it's going to be square root summation of I equal to 1n xi minus x bar squared, and then summation of I equal to 1 up to n yi minus y bar squared. So yeah, that is the That is the what? That is the definition of correlation. So correlation is basically a measure of linear relationship between x and y, right? It's just a measure of the linear relationship between x and y. And this sounds like our R squared, because R squared is trying to measure also the relationship between two quantities, our y and our x. Let's just say our two quantities in this case, y and x, right? So one might then say, but correlation already does that, because if you've done statistics before, but correlation already sees how two quantities are related to each other. Let's call this small letter r. It actually, what do you call this? It actually turns out that in simple linear regression, our R squared that we calculate using our TSS and stuff like that is equal to correlation squared, correlation between the two squared. So someone can use correlation if you want. You can use the correlation, or you can use this R squared that we have just discussed here. We are now going to get into something called multiple linear regression. We have talked about simple linear regression. Simple linear regression was just saying y is equal to beta naught plus beta 1x, right? Or sales is equal to beta naught plus beta 1 TV advertising budget. But in our advertising data, we have radio as well. And we have newspaper advertising. Where are those going to come in? Where are those going to come in? Why did we choose TV only? Radio advertising also affects our sales. Newspaper adverts might affect sales. Where are those coming in? That's what we are going to get into now. It's called multiple linear regression. And when we get into multiple linear regression, this stops holding. It doesn't hold in multiple linear regression. But let's get into that and see what it's all about.